Welcome to QubitInk. This video begins our discussion of quantum algorithms. The focus is classical computation, quantum parallelism, Deutsch's algorithm, and the Deutsch-Jozsa algorithm. We are not yet trying to build large practical algorithms. We are first learning the mathematical pattern that makes quantum algorithms different. The key idea is that a quantum computer does not gain power by reading many branches of a superposition one by one. It gains power by arranging amplitudes so that the final measurement reveals the property we care about. Video 2 ended with two fundamental protocols, teleportation and superdense coding. In teleportation, one shared bell pair, together with two classical bits, allows an unknown qubit state to be transferred. This does not mean copying the qubit. It means reconstructing the state at the receiver after measurement and classical communication. Superdense coding reverses the resource logic. With one shared bell pair, sending one qubit can communicate two classical bits. These examples show that entanglement is not only a strange correlation. It is an operational resource for information processing. The central question is whether a quantum computer can solve some computational tasks with fewer steps. The slide gives the three ingredients: superposition, phase, and interference. Superposition means that a state vector can contain many computational basis states at the same time. Phase means that information can be stored not only in probabilities, but also in signs and complex phases. Interference is the crucial step. Amplitudes can cancel or reinforce. Quantum speedup comes from controlling this interference before measurement, not from directly reading every computational branch. The roadmap moves in a logical order. First, we explain why classical logic must be embedded into reversible quantum gates. Then we introduce oracles, which allow a classical function to be queried inside a quantum circuit. After that, we study quantum parallelism, where the oracle acts on a superposition of inputs. This leads to Deutsch's algorithm and then to the Deutsch-Jozsa algorithm. Finally, we place these examples into the broader algorithmic landscape: Fourier methods, search algorithms, and quantum simulation. A quantum gate maps a state ket psi to U acting on ket psi. The matrix U must be unitary, so it satisfies U dagger U equals I. Here, U dagger is the conjugate transpose of U, and I is the identity. This condition has a strong meaning. It preserves normalization, total probability, and inner products. It also gives U inverse equals U dagger, so the operation can be reversed. Classical gates such as AND and NAND may erase information, so they cannot be used directly as quantum gates before measurement. They must first be embedded into reversible transformations. The Toffoli gate is a reversible 3-bit gate. It sends A, B, C to A, B, C XOR A times B. The first two bits are controls. The third bit flips only when A equals B equals 1. The symbol XOR means addition modulo 2, or XOR. The identity T squared equals I tells us that applying the Toffoli gate twice gives the original input back. This is why it is reversible. With an ancilla initialized to ket 0, the gate maps A, B, 0 to A, B, A times B. In this way, the AND operation is computed without erasing the input bits. Now we take a Boolean function f maps AND bit strings to one bit and represent it inside a reversible quantum operation. The oracle is written as U sub f acting on ket x ket y equals ket x ket y XOR f of x. The first register stores the input x, and the second register is the target. If the target starts as ket 0, then the oracle gives ket x ket f of x. If the input is a superposition, linearity applies. Each branch ket x is transformed coherently, with the same amplitude alpha sub x, into ket x ket f of x. This slide shows the standard circuit notation for the oracle U sub f. The upper wire is the input register ket x, and the lower wire is the target register ket y. The oracle leaves the input register unchanged and writes the function value into the target by modulo 2 addition, U sub f acting on ket x ket y equals ket x ket y XOR f of x. This form is important because it makes the operation reversible. The input is not destroyed. The target changes in a way that depends on f of x. In query complexity, the oracle is treated as a black box, and we count how many times it is used. The Hadamard gate changes the computational basis into a superposition basis. It maps H acting on ket 0 to ket 0 plus ket 1, divided by the square root of 2. It maps h acting on ket1 to ket0 minus ket1, divided by the square root of 2. The minus sign is not a small detail. It is the beginning of interference. For n qubits, applying h tensor n to ket0 tensor n gives 1 over square root of 2 to the n, sum over x in the set of n bit strings ket x. Thus, only n Hadamard gates create an equal superposition over 2 to the power n basis states. We start with ket0 tensor n ket0. The first register contains the input, and the second register is the target. After applying h tensor n to the first register, we obtain 1 over square root of 2 to the n, sum over x ket0. This is a superposition over all computational basis inputs. Now the oracle acts once, 1 over square root of 2 to the n, sum over x ket0 maps to 1 over square root of 2 to the n, sum over x ket f of x. The function has been evaluated coherently across all basis inputs. This is quantum parallelism. The state after the oracle is 1 over square root of 2 to the n, sum over x ket f of x. It is tempting to say that we now know all values of the function. But that is not correct. A standard measurement in the computational basis gives only one outcome pair, x, f of x. One run reveals one branch. Therefore, quantum parallelism alone is not a complete algorithmic advantage. The goal is to design a circuit where the branches interfere before measurement. Then the measurement can reveal a global property of f, rather than a single value of f of x. Prepare the target qubit in ket minus, which is ket0 minus ket1, divided by the square root of 2. Now apply the oracle. The target becomes ket0 xor f of x, minus ket1 xor f of x, divided by the square root of 2. If f of x equals 0, nothing changes, and the target remains ket minus. If f of x equals 1, the two basis states are swapped, which turns ket minus into minus ket minus. Therefore, u sub f acting on ket x ket minus equals minus 1 to the power f of x ket minus. The function value has become a sign on the input branch. This is phase kickback. Deutsch's problem considers a Boolean function f maps 1 bit to 1 bit. There are 4 possible functions. 2 are constant, both inputs give the same output. 2 are balanced, the 2 inputs give different outputs. The quantity f of 0 xor f of 1 summarizes the answer. If it is 0, the function is constant. If it is 1, the function is balanced. A deterministic classical method must query both f of 0 and f of 1. Deutsch's algorithm shows that a quantum circuit can determine this global property with one oracle call. The circuit begins with 2 qubits, ket0 and ket1. A Hadamard gate is applied to both. The first qubit becomes a superposition of the 2 possible inputs. The second qubit becomes ket minus, which is the target state needed for phase kickback. The oracle u sub f is then applied once. After the oracle, a final Hadamard is applied to the first qubit, and that qubit is measured. The measured value is f of 0 xor f of 1. Therefore, one measurement distinguishes constant and balanced functions. The input state is ket psi sub 0 equals ket0 ket1. After 2 Hadamard gates, the state becomes ket psi sub 1 ket0 ket1 over square root of 2 ket0 minus ket1 over square root of 2. The second factor is ket minus. After the oracle, phase kickback gives ket psi sub 2 fraction minus 1 to the power f of 0 ket0 plus minus 1 to the power f of 1 ket1 square root of 2 ket minus. If f of 0 equals f of 1, both branches have the same sign. If f of 0 not equal to f of 1, the branches have opposite signs. The last Hadamard converts the phase relation into a computational basis result. It maps ket0 ket1 over square root of 2 to ket0, and it maps ket0 minus ket1 over square root of 2 to ket1. Therefore, after the final Hadamard, ket psi sub 3 equals plus or minus ket f of 0 xor f of 1 ket minus. The overall plus or minus sign is a global phase, so it does not affect the measurement. If the first qubit is measured as 0, the function is constant. If it is measured as 1, the function is balanced. A classical deterministic method needs 2 function calls. Deutsch's algorithm needs 1. This slide separates the 2 possible cases in Deutsch's algorithm. For a constant function, both computational branches acquire the same phase, minus 1 to the power f of 0 equals minus 1 to the power f of 1. So the first qubit is proportional to ket 0 ket 1 over square root of 2. The final Hadamard maps this state to ket 0. For a balanced function, the two branches acquire opposite phases, -1 to the power f of 0 equals -1 to the power f of 1. Then the first qubit is proportional to ket 0 minus ket 1 over square root of 2, and the final Hadamard maps it to ket 1. The algorithm works by converting phase information into a measurable bit. This picture summarizes Deutsch's algorithm as an interference process. In the constant case, the two paths carry the same phase. They recombine through the final Hadamard and produce the output ket 0. In the balanced case, the two paths carry opposite phases. They recombine differently and produce the output ket 1. The important point is that the answer is not read from one computational branch. It is produced by recombining branches. Deutsch's algorithm is therefore a minimal example of the quantum pattern: encode information into phase, interfere amplitudes, and then measure. The Deutsch-Jozsa problem generalizes Deutsch's problem from one input bit to n input bits. Now the function is f maps n bit strings to 1 bit. There is a promise. The function is either constant or balanced. Constant means that f of x equals 0 for every x, or f of x equals 1 for every x. Balanced means that exactly half of the inputs give 0 and exactly half give 1. #x, f of x equals 0 equals #x, f of x equals 1 equals 2 to the power n minus 1. The task is to decide which case holds, using as few oracle calls as possible. The Deutsch-Jozsa circuit has the same structure as Deutsch's algorithm, but now the first register contains n qubits. We start with ket 0 tensor n ket 1. The first register receives h tensor n, and the target qubit receives h. The oracle u sub f is applied once. Then h tensor n is applied again to the first register. Finally, we measure only the first register and obtain a string z in the set of n-bit strings. The target qubit is not measured. Its role was to create phase kickback. The input state is ket psi sub 0 equals ket 0 tensor n ket 1. After applying h tensor n to the first register, every possible n-bit input appears with equal amplitude. The target qubit becomes ket minus equals ket 0 minus ket 1 over square root of 2. So the state is ket psi sub 1 1 over square root of 2 to the n, sum over x in the set of n-bit strings ket x ket minus. This is the correct setup for phase kickback. The first register contains all 2 to the power n possible inputs, and the target is ready to turn function values into signs. The oracle now acts on the state ket x ket minus. By phase kickback, u sub f acting on ket x ket minus equals -1 to the power f of x ket minus. Therefore, after one oracle call, ket psi sub 2 1 over square root of 2 to the n sum over x minus 1 to the power f of x ket minus. The truth Toffoli is no longer written into a target bit. It is encoded as a phase pattern over the input register. If f of x equals 0, the branch receives sign +1. If f of x equals 1, the branch receives sign -1. The next Hadamard layer will make this phase pattern interfere. This slide gives the exact interference formula. For 2-bit strings x and z, the dot product is .z equals x sub 1 z sub 1 plus x sub 2 z sub 2 plus plus x sub n z sub n modulo 2. The n-qubit Hadamard transform satisfies h tensor n ket x 1 over square root of 2 to the n sum over z minus 1 to the powers .z ket z. When this is applied to the phase-encoded state ket psi sub 2, the amplitude of each output string z becomes 1 over 2 to the power n, sum over x minus 1 to the power f of x plus .z. This sum is where the interference happens. To understand the output rule, focus on the amplitude of the all-zero string ket 0 tensor n. For z equals 0 to the power n, the dot product's .z is 0 for every x. So the amplitude is a sub-0 to the power n 1 over 2 to the power n, sum over x minus 1 to the power f of x. If f is constant, then every term in the sum is +1, or every term is -1. Hence the amplitude is +1 or -1, and the probability of measuring 0 to the power n is 1. If f is balanced, half the signs are +1 and half are -1, so the amplitude is 0. Therefore, measuring 0 to the power n means constant. Any other output means balanced. The output rule is very simple after the mathematics. Measure the first register. If the result is 0 0 0, then the function is constant. If the result is anything else, then the function is balanced. The histograms illustrate this difference. For a constant oracle, all probability is concentrated on the all-zero output. For a balanced oracle, the all-zero output is absent, and the probability appears on some non-zero string or strings, depending on the specific balanced function. The result is exact under the Deutsch-Jozsa promise. This Toffoli compares deterministic classical queries with quantum queries. For Deutsch's problem, a deterministic classical method needs 2 queries, while the quantum algorithm needs 1. For the Deutsch-Jozsa problem, a deterministic classical method needs 2 to the power n-1 plus 1 queries in the worst case. This is because after seeing 2 to the power n-1 identical outputs, the function could still be balanced. 1 more query is needed to decide with certainty. The quantum algorithm uses 1 oracle query. This is a query model speedup. The oracle is treated as a black box, and the cost is the number of times that black box is called. This slide abstracts the pattern behind Deutsch and Deutsch-Jozsa. First, initialize the system. Second, create a superposition, ket 0 tensor n zritaro h tensor n sum over x ket x. Third, use the oracle to write the function into phases, sum over x ket x zritaro u sub f sum over x minus 1 to the power f of x ket x. Fourth, apply interference, usually through another structured transform such as h tensor n. Finally, measure. The answer is not the full list of function values. It is a measurably global property. This pattern is the seed of Fourier-based algorithms and phase estimation. After Deutsch and Deutsch-Jozsa, the algorithmic landscape expands into 3 main directions. The first is the Fourier family, which includes Deutsch-Jozsa, phase estimation, and Shor's algorithm. These algorithms use structure and periodicity. The second is the search family, centered around Grover search and amplitude amplification. These algorithms provide a quadratic speedup for unstructured search. The third is quantum simulation, where quantum computers are used to model quantum systems such as molecules, materials, and many-body dynamics. These families are central because they represent different ways quantum mechanics can help computation. This wider map organizes the next stage of the field. Fourier and period finding methods lead to phase estimation, order finding, and Shor's factoring algorithm. Search and amplitude amplification lead to Grover's algorithm, quantum counting, and optimization subroutines. Quantum simulation leads to applications in chemistry, materials science, and many-body physics. Deutsch and Deutsch-Jozsa are the first examples, not because they are the most useful practical algorithms, but because they reveal the central mechanism. Quantum algorithms exploit structure, search geometry, or physical simulation in ways that classical computation cannot directly copy. Many quantum algorithms are not designed to list all values of a function f of x. They are designed to reveal a hidden pattern in the way the function behaves. The quantum Fourier transform is one of the main tools for doing this. It maps a basis state ket j to 1 over square root of n, sum sub k equals 0 caret n 1 e squared pi I j k slash n ket k. This transformation changes from a position-like description to a frequency-like description. Deutsch-Jozsa extracts constant versus balanced structure. Phase estimation extracts an eigenphase. Order finding extracts a period. Shor's algorithm uses that period to find factors. Phase estimation begins with an eigenvalue equation, u acting on ket u equals e squared pi I phi ket u. Here, ket u is an eigenstate of the unitary operator u, and the eigenvalue is a complex phase. The task is to estimate phi. The circuit uses an auxiliary register initialized to ket 0 tensor t, controlled powers of u, interference, and the inverse quantum Fourier transform. The output is an estimate ket y tilde phi, while the eigenstate ket u remains. Phase estimation is central because it turns phase, which is normally hidden in amplitudes, into measurably classical information. Shor's algorithm reduces factoring to order finding. Suppose we want to factor an integer n. For a chosen integer a, the order r is the smallest positive integer satisfying a to the power of r is congruent to 1 modulo n. The quantum part of Shor's algorithm finds this period using the quantum Fourier transform or phase estimation. Once r is known, the factors may be obtained from GCDA to the power r over 2-1 n, GCDA to the power r over 2 plus 1 n, when the usual number theoretic conditions are satisfied. The important point is that the quantum computer does not directly try every possible factor. It finds hidden periodic structure. Grover's algorithm addresses unstructured search. Suppose there are n possible items, and an oracle marks the good item. A classical search needs order n oracle queries in the worst case. Grover's algorithm needs approximately order square root of n queries. It begins with the uniform superposition ket s equals 1 over square root of n, sum over x equals 0 caret n1 ket x. The algorithm repeatedly applies reflections. One reflection marks the solution through the oracle, and the other reflects about the average amplitude. Repeating this process increases the amplitude of the marked state and decreases the amplitudes of the unmarked states. Grover's algorithm has a clean geometric interpretation. Although the Hilbert space may be very large, the important motion takes place mostly inside a two-dimensional plane. One direction corresponds to the marked state. The other corresponds to the average unmarked direction. A Grover step is written as G equals 2 ket spra si O sub f. Here, O sub f is the oracle reflection, and 2 ket spra si is the reflection about the uniform state ket s. The product of two reflections gives a rotation. Each Grover step rotates the state closer to the marked solution. Quantum simulation is motivated by a simple and powerful idea: use a control-oblique quantum system to imitate another quantum system. The time evolution of a closed quantum system is written as ket psi t equals e caret iht ket psi 0. Here, h is the Hamiltonian, and it determines the system's dynamics. Classically, a general n-qubit state requires 2 to the power n complex amplitudes to describe. This exponential growth makes many quantum systems difficult to simulate on ordinary computers. A quantum device can represent the state directly using n qubits. This is why quantum simulation may become one of the first scientifically useful applications of quantum computers. In digital quantum simulation, the Hamiltonian is decomposed as h equals sum sub l equals 1 to the power of lh underscore l. The full evolution is e caret iht. When the terms h underscore l do not all commute, we approximate the full evolution using short time pieces. E caret iht is approximately e caret ih sub 1 ton per r e caret ih sub 2 t slash r dot dot, e caret ih sub lt slash r caret r. This is a product formula approximation. The parameter r controls how finely the time evolution is divided. The simulation problem becomes a circuit synthesis problem. Implement these short time evolutions using abyl oblique quantum gates. The simulation workflow has 5 steps. First, choose the physical model. Second, encode the state into qubits. Third, implement the time evolution operator e caret iht. Fourth, measure observabless. Fifth, estimate the physical quantity of interest. Examples of observabless include angle bracket z sub e angle bracket x sub 9 sub j angle bracket angle bracket. These are expectation values, not full wave functions. This point matters. In most quantum simulations, the final answer is not the entire state vector. The goal is usually to estimate measure oblique quantities such as energy, magnetization, correlation functions, or other physical observabless. This video followed a chain of ideas: reversible logic, oracles, phase kickback, interference, and algorithmic advantage. Reversibility is required because quantum evolution before measurement is unitary. Oracles allow classical functions to be queried inside quantum circuits. Phase kickback writes function values into signs. Interference converts those signs into measurably outcomes. Deutsch and Deutsch-Jozsa show this pattern in its simplest form. The broader families, Fourier methods, Grover search, and quantum simulation, build on the same principle. Quantum algorithms shape amplitudes so that measurement reveals useful global information. The next video slows down and builds the mathematical foundation more carefully. We will begin the foundations of quantum mechanics, linear algebra, state spaces, operators, measurement, tensor products, density matrices, and the postulates of quantum mechanics. These tools are not optional background. They are the language in which quantum algorithms are written. Up to this point, we have used the notation operationally. In the next video, we will explain what that notation means, how quantum states are represented, how measurements are described, and how multi-qubit systems are constructed. The main source for this video is Michael A. Nielsen and Isaac L. Chuang, Quantum Computation and Quantum Information, 10th Anniversary Edition, published by Cambridge University Press. This text remains one of the standard references for quantum computation and quantum information. The implementation material for the demos is based on IBM Quantum Learning material on Deutsch-Jozsa and Qiskit-based tutorial notebooks for quantum algorithms. These references support both the mathematical development and the computational demonstrations used in this video. Thank you for watching QubitInk. This video introduced the first algorithmic ideas in quantum computation, quantum parallelism, phase kickback, interference, Deutsch's algorithm, Deutsch-Jozsa, and the wider map of Fourier methods, search, and simulation. The main lesson is that quantum algorithms do not work by exposing every branch of a superposition. They work by arranging amplitudes so that the final measurement reveals a useful property. In the next video, we will step back and build the mathematical foundations of quantum mechanics carefully, one idea at a time.